Today's lecture is all about how to make big models smaller and better. So we all know that like LLMs are useful and they're big, but training big models is really expensive. It takes a lot of CO2 and a lot of money. Um, and then, but it's kind of surprisingly, inference is even more expensive. So this is kind of I think Graham might actually disagree with this estimate, but there's a suggestion that ChatGPT every week is more costly than the amount of money it took to train it, which is kind of absurd. So there's a very natural question of how can we get the benefits of something like ChatGPT without paying that much money for inference cost. And models are, I guess now they're starting to plateau somewhat in terms of size, but they're still getting bigger, and usually the bigger models perform better. And so the question today is, how can we cheaply and efficiently deploy NLP systems that are still really effective? And so the main takeaway here, and what I'll talk about today is, excuse me, you talking is bothering me. So the main takeaway is, how can we compress models for better inference? And there's three approaches that I'll talk about today. They're quantization, pruning, and distillation. So quantization is you take a model that's really big, but you just like make it lower fidelity in terms of the way it's represented on hardware, and that can actually lead to a lot of speedups. Pruning is you actually like reduce the model architecture, so you might maintain the same fidelity, but you actually change the model. And then distillation is you train a smaller model to emulate a bigger model. And distillation is kind of what most of my research is about. So that's what I want to talk about mostly, and what I'll spend most of the time on. So there's a natural question here of why any of this is even possible. Like it might seem surprising that you can take a big model and make it smaller and expect it to not be really bad. And I think that the way I think about this is that having these huge language models is really a training time strategy, because when you have many more parameters than you have examples, or when you have like over parameterized models, it makes it easier to train a model to do really complicated things. But ultimately, this is useful at training time. And if you want to know more about this, convex optimization gives a really good intuition for why this is the case. But then once you've like kind of optimized your model into the right part of the weight space, you don't really need 100 billion parameters anymore. You might need a lot fewer. And so that's kind of why I think any of this even makes sense. Okay, so I'll now jump into quantization, but are there any questions about the motivation here so far?
Like when you're reducing these with the size of these models, like does that have an effect on, say, in context learning or things which happen in inference?
Yeah, the question is if compressing a model might affect how you do inference or like things like in context learning. Yeah, definitely. I think that there are definitely trade-offs. You accept probably lower performance by compressing a model. But I think that there's a lot of evidence that you could compress a model and still maintain in context learning ability and things like that. Yeah, I'm not sure if I'll actually go into that specific aspect, the in context learning part. So if you have more questions, please ask me at the end. Okay, so the first, like most obvious way to compress a model is just to like take this gigantic model that you trained and then quantize the weights. So if you have a model that was trained with 4 bytes, maybe you can throw away some of those bytes and then represent it in a more on a smaller footprint. So this reduces the amount of disk space it requires, but also the amount of memory it requires when you load the model in. And to understand this, I think that we need to understand how floating point numbers work. And so this is probably a review for many of you who, if you studied CS or EC in undergrad. But floating point numbers are stored a little bit differently than, say, integers, which are that there's a sign bit, a fractional part, which is, and then the fractional part is then multiplied by an exponential part, which allows the model, this representation to represent either really big or really small absolute values. And so where this matters for machine learning is that in machine learning, what you often care about is representing really small values. And so therefore, you're sometimes willing to throw away some of the ability to you might throw away some of the different allocations of values in the middle of your representation to be able to represent really big or really small values. And so this is why there's something called bfloat 16, which is like a very popular replacement for the float now, which it gives the representation ability to capture very small or very large float values in exchange for having a smaller fractional part of the float. And so this is like maybe the first way that like by doing this with the same 16 bits of representation, you can get a lot more performance. But this still might be a lot. So if you have, as we showed here, if you have 2 bytes, a 65B model is still 130 GB on memory, which is probably too big for most people to use. So a very natural thing to do is to like, okay, can we just can we take this representation and then just squash it into a much smaller space? And so one popular way to do this is called int8 quantization, where you basically you take all of your weights at a certain dimension, and then you look at what the biggest one is, what the smallest one is, and then you basically interpolate all those values into one of like, say, 256 buckets. So instead of having like this virtually unbounded space of values, you're now compressing everything into one of 256 values. And this actually kind of works. And so I'll give an even more extreme example here, which, or this kind of works, but there's some downsides that we'll go into. So the most extreme case is if instead of having int8 quantization, we had just binary quantization, where imagine we have this full precision model that has this embedding layer and this feed forward layer, and each of these parameters is a float here. But what if I just rounded everything to the nearest whole number, so it was 0 or 1? This would be like the most extreme imaginable quantization. The problem here is that if we take a trained model and we do this, which is called post-training quantization, you might end up with things rounding in such a way that you like result in the same word every time, or you're losing a lot of the actual representation ability of that model by like squashing things together. And so hopefully this motivates why like post-training quantization like this is not that easy, and you might need to be clever with how you do this. So the first kind of clever observation people have made that makes quantization work is that, so the way I presented it before is that like the most naive way of quantizing is say everything less than 0.5 becomes like goes into the 0th quantile, and everything above 0.5 goes to the first quantile. And you might think of the same way if you have 128, if you have a larger number of categories where you just divide things uniformly. But in fact, weights tend to be distributed in a more predictable way. So here in this paper showed that for BERT, the weights tend to lie on a Gaussian. And so if you were actually to like split things up uniformly, you would be having a bunch of these categories that have probably nothing in them, and then a few of these will contain almost all of the values. And so practically you're like having a really coarse quantization in a much more expensive representation space. And so this paper, what they suggest to do is that they first quantize like the body of this distribution according to the density of it. So like that things in the middle might have really small buckets and things outside might have bigger buckets. But then the tail of this distribution, which in practice might be very few parameters in the model, they don't even quantize. So they say like, okay, we'll pay this like full cost of storing this in memory for a very small number of parameters for which it's like maybe hard to quantize them, and then everything else we will quantize. So that way you're not applying the same. You're accepting that some parameters are much more important to the model to represent fully, and I think that this method is really effective and has been used a lot since then. Any questions?
Says 8 buckets, does it still mean 8-bit quantization?
Yeah, I think I meant to say 8 bits here. I think that was a typo for me. Yeah, but I'm not actually exactly sure. Cool. Yeah. So the basic idea here is that some parameters you want to quantize, some you don't want to, and the ones you quantize according to the way the weights are distributed, rather than doing like a one size fits all.
B-flow can store bigger values instead of more precise values.
Yeah, exactly.
So
bigger and smaller,
and small.
like close to 0 or close to like infinity.
I thought it was just because, so I was wondering all the weights are close to 0, then why are we?
Oh, I see. Yeah. So with B float here, this exponent can be positive or negative, and so you can have very negative exponents or very positive exponents.
In that model-aware quantization, how do we decide which weights are more important to not quantize? Like you said that the weights that are rare are also the ones that are important.
Yeah, I think that if I recall correctly, they do this by they have like a validation set and they run the forward pass of this model and then look at the activations, and then the layers where yeah, I don't remember exactly the details there. I'm sorry. Okay. So is that nowadays we're almost all using works to train and serve our models, and the quantization. So you might have like want to do 3-bit int3 quantization, but there's like no frameworks that will support that. So for like say a transformer model, will only support where's this? Yeah, there are only certain data types that are supported, like int8 is supported, int4 is not supported. So this is something you want to think about. If you're doing quantization, like you want to think about the actual framework they're using and whether it supports that quantization setup. So like this Gobo paper, they wrote their own hardware accelerators to bypass this, and this is a solution, but it's a lot of work. So this is something as a practitioner, you'll want to think about this in terms of what level of quantization is actually going to translate to real. Like if you do int3 quantization, but then you end up representing it as int8 in anyways, you're not getting any gains from it. And so you do want to think about what your actual deployment constraints would be. Okay, so hopefully I've convinced you to some extent that post-training quantization is like kind of hard and in some ways fundamentally limited. So I think a much more clever way is, which is becoming very popular, is quantization aware training. And I'll talk about primarily two ways to do this. So the first idea, earlier I showed a binary neural network where we took like a trained model and then we just squashed all the weights to 0 or 1. And I showed that it kind of was very flawed. But instead, if you took a binary neural network and trained it from the beginning to be binary, this can actually be really effective. So I'll skip the details of this, but they had to do some clever tricks to actually train this model, because binary variables might be hard to like, they're not maybe differentiable. And so there are certain tricks that they use to make this work. But the main takeaway that I want to show here is that for these here they do the image classification tasks, a binary neural network was able to achieve like kind of shockingly good performance, like 98% accuracy on MNIST, or which MNIST is kind of easy, but like 97% on this street view house numbers classification, despite being like one fraction of the size of the best models of that time. So hopefully the takeaway here is that you can actually, if you think about quantization from the beginning, you can do a lot with that. And one way that you can do this is you can initialize you can take a model and then you now want to quantize it. So you can sort of distill a quantized model from the full model. So for each layer, you now want the weights to fit within a certain discrete set of categories rather than to be like any float value. But then you train that layer to mimic its unquantized counterpart. And so here it's sort of actually more like post-training quantization, where you take a model that you trained and then you layer by layer train a quantized version of that layer to mimic the behavior of the unquantized counterpart. So this is basically like layer by layer distillation. And I think this is really an effective method, and it's kind of intuitively, it makes intuitive sense as well. And then probably the most popular one right now is QLoRa, which I think Graham has already talked about. Is that right? Or if not, he will. Which they do also quantization aware training, and they do some clever hardware some clever memory management tricks to make this work. QLoRa, by the way, was written by Tim Detmers, who's joining CMU in the fall. So okay, so this is all I'm going to talk about for quantization. Are there any questions before I move on to pruning?
For distillation, like the paper before this, you said you do it after the quantized model is already, like the original model is trained, but you said that the quantization during training is better. According to this,
Yeah. So yeah, I think that I see why that was confusing. Here, this is actually training a model from scratch, but the model is being supervised by the unquantized model rather than by the original data. So you could think of it as quantization aware training, but just with a different data set than what the original model was trained on. Whereas QLoRa is something you actually train on your raw data using QLoRa, using like the 4-bit quantization. Okay, so moving on to pruning. So pruning is, I think, it's conceptually really simple to understand. You take a neural network which has different layers and different weights, and then you just throw away many of these layers or weights. So you can like set them to 0, basically. And by setting them to 0, you don't have to represent them in memory, and it lets you do inference with smaller memory and faster because you're doing less computations. And so just to distinguish pruning versus quantization, in pruning, without like unquantized pruning, you're completely eliminating some parameters, but the rest are unchanged. Whereas in quantization, almost all parameters are changed, but only up to a certain number of bits of precision. So that's just to distinguish this from the previous section here. So the kind of the most obvious way you might do pruning is to look at the parameters that are the smallest and get rid of them. Like if you have a let's say you have an embedding matrix and you have certain dimensions that are almost always zero, it might stand to reason that those dimensions are kind of falling within the cracks of your training procedure, and therefore they might not be representing much meaning, and you can just get rid of them. So this approach is called magnitude pruning, where you just choose a certain number of parameters you want to get rid of, and then you look at the individual weights of your neural network that have the least magnitude and just throw those away up to X%. This is known as unstructured pruning, where you're just choosing parameters with indiscriminately across your entire network, rather than choosing them to be all from the same, say, layer or the same matrix. So Wanda, which was written by people at CMU recently, is similar to magnitude pruning, where they make the observation that what matters is not just the size of the weights, but how you can scale the magnitude of the weights by the activation from that layer. And so if you have a parameter that has a very small average magnitude, but that has a right. So if you have multiple layers in a network, then the activation will affect how much that layer actually goes into the next one. And so therefore, they suggest that what you need to look at is not just the absolute values of your weights, but also how much the scale of those activations, because those two things together will determine how much that parameter affects the overall prediction. But these are just two different simple ways of choosing which parameters to zero out. I think that ultimately, I think both these methods have a fundamental flaw, which is that unstructured sparsity, just like zeroing out certain parameters, doesn't actually really help at all. Because ultimately, when you're doing neural network inference, you're using matrix multiplications, and unless you have like very specialized sparse data types, you might be doing the same amount of work on your GPU, even if like half of the entries in your matrix are zero. It might not translate at all to any real speedups. And so this can be useful if you have some kind of specialized hardware that supports like sparse data types. Then this can be really useful. But for like the kinds of things you're probably going to be using in your research or in industry, for the most part, I think that unstructured pruning is not that useful. So instead, structured pruning is the idea of removing entire components. So you might remove attention heads or remove entire feed-forward layers, and based on how much those affect the prediction. And so this way you're like removing entire matrices from your model, and that will very easily translate to actual speedups at inference time. So you choose components to prune out, and the rest of the components are completely untouched. One extreme example of this was some work by Graham a few years ago, by one of Graham's students, Paul, a few years ago, where they showed that at that time, in BERT, which was the main model at the time, there were 16 attention heads, but they showed that you could bring it down to just 2 or 3 and achieve almost exactly the same performance. But you had to do this after training. So this would be like another example of structured pruning. And then lastly, one problem with structured pruning in general is that you require a lot of memory. So you often are, yeah, so to prune a big model, you basically need to have enough hardware to train that model. So imagine you take Llama 370B. You might have enough compute to do inference in that model, but you might not have enough compute to train that model. And that means that most existing methods for structured pruning won't work because you can't store the gradients of your entire model. So a paper by Lucio, who's one of Graham's recently graduated students, they propose to use just the forward passes. So basically you randomly mask out certain components. So you might mask out attention heads and maybe some layers, and then you perform predictions using these different randomly like masked versions of the same model. And now you effectively have a data set that shows how much masking out each component affects the overall performance. And the downside being that because you're randomly masking things, you don't have, and there's many different components in the model, you don't have like every possible combination of maskings represented. So you use machine learning you train a regression model to basically predict what the impact of masking out each component is. So this way they like don't have to do any training. They basically collect a data set of how much masking each component might affect performance, and then they approximate the actual effect of masking out each component, and then use this to do the actual masking. So this is called pruning with forward passes, and I think it's a really nice idea. So as you can see here, just to put a bow on the pruning part of this, Wanda, which was the second unstructured pruning method I showed, even though a model here is like a small model from Wanda may not actually have any speedups. Whereas Bonsai, which is the pruning with forward passes method, this is a structured pruning method, and for the same size, it gets like a 60% speed up. So the point of me showing this is that showing why structured pruning might be more effective in practice. Okay, so now I'm going to move on to distillation, but I want to stop and see if there's any questions.
So when you say like you would remove entire components, so does that mean like if you have an XW, you just remove the W and like X is like propagated as it is?
Yeah, I think that you can think of it as just the W becomes zero. Yeah.
Like, wouldn't you probably need like fine tune after that or something, or like is it expected to work out of the box like that?
I think that's a great question. Yeah, so I think maybe what you're getting at is that if you remove entire components, it might be changing the statistics of how you might be changing the distribution of the input to each layer, like maybe yeah, I think that's a good question. I think in this paper they just use Llama, the language model, out of the box without any additional fine tuning, and it still works. But yeah, I think that's a really good question. Any more questions on pruning before I move on?
You remove entire components, then like just said that you set the waste to zero, and like you're still gonna have to do some sort of computation there, right, to account for the fact that like the shape with the component and the shape without the component
I
is
see.
different. So like
Yeah.
uh, changing or adjusting the shape would also come with its own like computational overhead, right? So, like, I'm wondering if like there's some sort of like, trade-off or something between the two. Or...
Yeah. So yeah, so I think you bring up a good point, which is that the if you were just to remove, say, an individual matrix in multi-head attention, you might change the shape of the output there and like somehow make this model not well formed. And so you would have to choose. So I think that the solution to structured pruning is to remove components that can be removed without affecting the shape of without violating the shape constraints. So like this, I think in practice, the things that are often done is either you remove entire layers where such that the input and output layer dimensions are the same, or you remove attention heads, which are, as Graham's paper showed, kind of somewhat expendable. Or you can remove dimensions of your embedding matrix, which then you have to change maybe something else in the next layer. But so just choosing the combinations of things you remove such that they maintain like such that all of the computations in your graph are still well formed. Any more questions on pruning? Cool. So now, yeah.
Each of the attention has like a portion of it in the output of this thing, right? So if the shapes of the input and output both match up to the entire attention.
Yeah, that is a good point. Yeah, off the top of my head, I don't remember exactly how that's handled. But I'll look into that and we can talk after class. So I'll move on to distillation now. And so the main idea of distillation, it's actually really simple. And we touched on it earlier in the quantization piece, which is that you train a student model to replicate the behavior of a teacher model. So in contrast with quantization and pruning, where large swaths of your model are unchanged, in distillation, virtually all of your parameters will get changed. And you might even have your student model be a totally different architecture. So it's much more flexible because it's basically you're just using the raw unquantized unpruned model as an oracle that comes up with more data. And so therefore what you do with that data is very flexible and up to the practitioner. So the original way the distillation was conceived was that the teacher works as a labeler. So like the student would give the teacher inputs. The teacher would then give back either labels or like probabilities on those of the output labels for those inputs. And then those like inputs and what are called pseudo labels from the teacher would then be used for training. So pseudo labels are basically targets that are generated for unlabeled text. So they might look like labels, but they're not written by a human. They're written by another model. And this idea is actually really old. So self-training, which is for 30 years old, is probably the original method where, and it's still kind of used today, where you have a model that produces predictions based on unlabeled data, and then you can use those same predictions to train that same model. This obviously has flaws, which is that the model might reinforce its own wrong predictions. Like if you have an input and the model struggles on, and then you train it on that same wrong prediction, it'll compound those errors. So I think that it's not used directly in the same way anymore. But yeah, so pseudo labels is the main idea behind this, using a model as a teacher. And there are sort of two kinds of pseudo labels, or two kinds of ways that this distillation is typically operationalize. The first is what is called hard target distillation, which is really easy to understand. You basically take a teacher model and have it generate discrete classes or discrete text based on your inputs. And then you can just treat these as like real data and just train a model just as you would with human annotated data. But one really nice thing about using a model as your teacher is that you can also get probabilities. So which actually gives you much more information. So if you have, let's say you have 3 classes and we're doing sentiment analysis, but your example is ambiguous and it could be neutral, it could be positive. The nice thing here is that the teacher might say, in this example, it's skewed, but the teacher might say, okay, give 0.1% of accuracy of confidence of probability to the positive class, and then split the remaining confidence equally among neutral and negative. And this kind of teaches the model something even greater, which is that either of these classes might be reasonable predictions. So I think the way you can think of this is that soft target distillation gives like a richer interface of communication between the teacher and the student model. And it works really well. So in this paper, they showed that using soft target distillation achieved substantially better test performance than using hard targets for a speech, I think. And I think that this still continues to be really a popular method. But one challenge is that nowadays with LLMs, we're no longer doing like direct classification as much. Like we often don't have a classification head. We typically are predicting words. And so how do we extend this kind of soft target distillation to sequence prediction? And so there is the way you might do this is to try to both learn the probability that the student model predicts the same okay, so taking a step back here, in this setup, we now have inputs, and then we have sequences generated by the teacher, and we can also have the teacher assign probabilities to sequences by the student. Right, so and we can use both these things. So we can first have the teacher generate its full answer. So maybe we're doing summarization and we give in Wikipedia articles and we have the teacher, maybe it's a Llama 7DB model and it produces entire summaries, which we can then train with a smaller BERT model on. But then we can have it match the probability of that, maximize the probability of that teacher's output. Then we can also have the student model predict each word at a time and have the teacher give it feedback on each of those words. So the teacher might say, you got the first 10 words pretty much right, but then the 11th word has a really low probability by the teacher's distribution. And so you can use both of these two kinds of signal, word level confidence from the teacher model, and then use the teacher model to generate full sequences. And both of these things are, I think, independently very useful for sequence level model distillation. Any questions here? And I think something that's like really surprising is that this idea of soft target distillation is so valuable that you can take a model and then have it generate the probabilities of the output space, and then train that same model on those same output on that. You can take a model and train it on the output of itself and improve that model. So I think so just to be more concrete here, you can have a procedure where you have multiple steps, and at each step, you take the model from the previous step, you generate predictions on unlabeled data, or labeled data, and then or the unlabeled part of labeled data, and then you can fine tune on to match the probabilities from the previous step. And this really surprisingly can be more effective than just using that model directly. I think that the reason this is surprising is they are actually not adding any new information here. You might take a model and a data set and then perform this procedure on that same model with the same inputs. So there's no additional information being added here. But I think that the yeah, so that's why I think this method is surprising. So far, everything I've shown was for like the pre-LLM world. And now we can start to extend these ideas more into a language that is probably more familiar to people who work with LLMs these days. So kind of similar to having word level distillation. I'll start with this one. You can have, nowadays, one really popular way for doing, for having LLMs do reasoning tasks is to produce a chain of thought. So you have, I'll do this. Okay, so taking a step back, nowadays there are many ways to break down a task into individual steps and then produce predictions for those individual steps and then put together the final answer. I think Graham has already touched on this, but there's a method called process supervision where you can take either a bigger model or a custom reward model that's been trained for this task and have it give feedback to the student model at each step of that reasoning process. The reason that this is interesting or valuable is that you often don't have real supervision at the step level. Like imagine you're trying to learn to do SAT math questions. You might have the final answer, but there is no answer key that contains the individual steps. And those steps might actually be unique to the student model. So the model might decompose your question in different ways. And therefore, you don't have natural supervision there, but you can take either a customized reward model or a big language model, and then have it give feedback to the student model of how good its answer was at each individual step. And this is called process supervision, which effectively unrolls. The way I think of this is that you're getting much more information for each example. Instead of just getting an supervision on whether your final answer was right, you're getting supervision at every step of your reasoning process. And then related to this, you can also have the teacher model generate both a label and a rationale and learn from both of these things separately as like a multitask learning setup. This also is a way of taking a teacher LLM and then having it give you additional supervision beyond just like the correct answer, but giving here like a rationale that you can also use for training. Okay, so but still none of these things are like really unique to LLMs. Rationales existed before LLMs, but I think that the really cool thing about distillation in the world of LLMs is that nowadays teachers can really like a teacher model can really effectively generate almost anything. They can generate they can generate outputs just as in the previous era of distillation. They can also generate inputs and outputs, so they can generate entire examples and any different combinations of this. One kind of clever way you might do this is that, this paper considers a task of open information extraction where you're given sentences from Wikipedia, and then you want to basically identify the entities that participate in this sentence. So triples of like maybe a location, like you have a movie and you want to identify what is the location of the movie and what is the name of the movie. And so this is actually a pretty hard task because it requires understanding all of the different components of the sentence and what role they play. But this paper makes the observation that the inverse of this task, which is given a triple and generating a sentence is super easy. Like you could actually just have a rule-based method to do this. But here they prompt an old version of GPT-3 to given triples from a knowledge base to generate sentences that use those triples. And now, so the basic idea here is that the task of interest, which is open information extraction, is hard. But the inverse task, which is to generate sentences using a triple of entities, is really easy. And so you can kind of work backwards and take the triples that you might extract, generate sentences, and now flip the order of this and train on. So even though you are sampling and these triples and generating sentences, you can now reverse the order of the data and now actually use what you just generated as the input for training your model to do the reverse direction. And this at the time, I think it still is like by far the most effective method for open information extraction. And I think that this idea is really interesting and something that LLMs enable you to do, which is that you can define how the data is generated by the teacher in a very flexible way using prompting. So you no longer have to just give in inputs and get out labels, but you can instead give in outputs and get back inputs, or decompose your task in whatever way you'd like. Any questions here? So one of the most widely used distillation methods or distilled models is called self-instruct, which was used to train Alpaca, which was like a sort of an open source GPT-3 competitor that used to be really popular. And here they actually distilled a LM they took a LM GPT-3 and then in the paper, which that version of GPT-3 was not instruction tuned, so it was just like a raw language model, and they wanted to see how can we. So GPT-3 was separately instruction tuned by OpenAI, but OpenAI did not release the data used for instruction tuning. So in this paper, they asked the question: if we have an LM and we want to instruction tune it, but we don't have instruction tuning data, can we have the model generate its own instructions and train on those instructions? So the way they did this was they started with a seed set of tasks instructions. Then they generated more instructions that looked like these. And then to do instruction tuning, you need both an instruction, but also like the right answer, like what the completion should look like for that instruction. So they had they did a clever way to get these completions from the LM. And then they then fine-tuned this GPT-3 model on these self-generated instructions. And this was almost as good as training on the largest existing instruction tuning data at that time. So I think this is evidence that like using LLMs as data generators can be really effective, especially for something like instruction tuning, where the task might not require a lot of new knowledge. It's more about how to process like the syntax or the specific intent of the user, rather than, you might not be able to do this if you had an LM that was only trained on English and you wanted to teach it Spanish, it's probably not going to be able to generate its own data for Spanish. But if you have a particular aspect of your data that you want to focus on, I think that's where this approach of using synthetic data can be really useful. So a few more, so some more recent work here. This is a paper that we wrote last year, which was combining here we consider the setup where you want to train a small expert model, and as in the classic distillation setup, you can just generate data from a teacher model, and this works. But we considered, what if you also like there's all this existing data on the internet. Many tasks have already been studied. Why not? Why are we leaving all this on the table? Like, why can't we? Is there a way that we can combine the existing work that researchers have done to generate data sets with using an LLM as a teacher? So in this paper, given a prompt written by a user, we first retrieved the most relevant existing data set from Hugging Face. We then generated data independently for this task. And I think the intuition here is that your retrieved data is likely to be of high quality, but it's potentially not going to match the user's intention. So you might be asking about question answering from Wikipedia articles, but you might retrieve something about question answering from academic publications. And so therefore, like they're pretty different in terms of domain, but the retrieved data hopefully will have been curated by a human, and it's likely to be high quality. And then you can generate data from the LLM to match the specific intent or domain of the user. And then we went a step further and also then retrieved the student model. So in the previous works I showed, the researchers hand chose the student model to train, but here we our system to identify if there were any pre-trained models that were maybe already pre-trained on your domain of interest to like give you a better starting point. And so then putting all these things together basically enabled us to get very strong models at a very small size. So for 3 tasks, we considered 3 tasks, and for 2 of them, we had 300 million parameter models that were outperforming GPT-3, which was 200 billion parameters. And some master's students who I worked with last year they extended this idea even further by doing what we call retrieval augmented distillation, where you first retrieve documents and then you like turn these documents into task-specific data, with the idea being that there might be some piece of information in each document that is relevant to the user's task, even if the user's task is completely new and novel. There might be something there that you can learn from. So this retrieved data could be entire data sets from Hugging Face. So in this paper, like one of the examples was that the task was the user the task in Big Bench Hard was given a piece of code, can you generate a description of that code? But we retrieved a data set for automatic code generation, which is sort of the opposite. And so we could then very easily automatically transform a code generation data set into a code explanation data set. Then taking this even further, you can retrieve from individual rows across many data sets. So this way, you're basically like just retrieving very unstructured examples that are curated by researchers, but each of them might be transformed in a totally different way, or they might consider a different language, a different, there might be a lot of diversity here, and that's something that you can actually benefit from. And then lastly, some works have also shown that you can literally just condition your generation on documents from the internet. So like concretely imagine you're doing question answering and you could retrieve passages and generate questions for those passages. The downside here is that I think that to make this work, you need to have documents that are very relevant to your task. Like they need to be in the same domain, definitely the same language. If we want to do Wikipedia QA and you retrieve a bunch of tweets from the internet, it's not going to be that useful. So the quality of your retriever here matters a lot. But that's why in these 2 papers, which I was part of, we retrieved from Hugging Face, where I think the level of quality is probably a little higher because they're designed for training models on. Cool. So now we're almost done here. Maybe the natural if you take by the way, I've been using this term synthetic data a lot, and I suppose that I haven't defined it properly. So distillation is where you use a model to teach another model. And if you're doing hard target distillation, the thing you use to train the model is called synthetic data because it just looks like data, but it was designed by a model, not a human. So there has been work that has pre-trained entire models based on synthetic data. So in your Min Llama data assignment, the model that we actually used for that assignment was trained on purely synthetic data. So in that model, that was from a data set called Tiny Stories, where they made the observation that real data has a lot of different vocabulary and a lot of entities, and therefore you might need a lot of parameters to be able to model that data, that text effectively. But if you instead prompt an LLM, if you just give it like 10 words and say, write me a story that has these 10 words, you can control the vocabulary very tightly while maintaining very fluent and potentially conceptually complex input. So this lets you get text that has a lot of richness, but is also simple to model in that it can be, you can use a small embedding matrix to store a small vocabulary. And so like, I think the model that you used in your assignment was something like, was in the tens of millions of parameters. And I think that would be really hard to do if you were using real data. But here, by using tightly controlled synthetic data, children's story data, it enabled you to actually generate coherent English. So this, like the data in your Min Llama assignment was kind of a toy data set, and it's probably not that useful, but that same team in Microsoft extended this same approach to real tasks. So you might be familiar with the Phi family of models from Microsoft, which are pretty small language models, and they in the Phi models are all trained on a small amount of or some real data that's been like very carefully retrieved to be of high quality, and then a significant amount of synthetically generated data that tries to basically mimic this and maybe fill in the gaps of what is in this retrieved data. And then it's instruction fine-tuned on more synthetic data. So I think in this specific plot was what was on code. So they take Stack Overflow questions, and if you just pre-train on those, you get kind of bad performance on human eval. If you add in synthetically generated code, your performance almost doubles. And then if you, for the specific task of doing code generation from descriptions, if you synthesize a lot of instruction tuning examples for this, you can like double your performance. So this is just to say that I think that pre-training on synthetic data has advantages, particularly if you want to have a lot of control over what your model sees. But I do think that where synthetic data is primarily useful is on fine-tuning your model for a specific task, like code generation, rather than just pre-training. Because for pre-training, there is a lot of data on the internet, and so you don't get as much value from using a teacher model. So lastly, a kind of interesting thought is that nowadays, a lot of data on the internet, a lot of text on the internet is already generated by language models. So a lot of Amazon Turk jobs are now actually done by language models because people want to get that Amazon Turk money, but in a lot less time. And so in some sense, there's kind of some unintentional distillation already happening where data is being generated by models and we're training on it without even realizing it or wanting to. And so in the most extreme case, imagine you are training a model iteratively, but at each step after the first step you train on a real data set. And the second step, you want to refresh your data set. You want to refresh your model on new data. And you maybe like crawl the internet again. But now here, the bots have taken over and almost all of this data is machine generated. And then, so this paper considers a more concrete version of this, where you have a feedback loop where you take a model that's a language model that's trained on real text. You then generate a bunch of synthetic text and then continue training that same model on this synthetic text. and you do this 8 more times. So you then generate more synthetic text, continue fine tuning on that text, and you do this after round. This specific version of this experiment I'm showing here is where they at each step they do keep 10% of the original data. But what you can see here is that at your first step, training on the synthetic data is actually really useful. It improves performance a lot. But then very quickly, the model plateaus and it becomes worse. I think that maybe the intuition behind why this is happening is that your model, what it generates starts to collapse into a small set of sentences or words that all occur very many times. So you lose a lot of the diversity that you might have had in your original data.
But it looks like it just saturates into like a certain number that's above the original complexity score. So it doesn't necessarily collapse, it more like just saturates to a certain number.
Well, it collapses from so I think the one thing I want to be clear about is that the performance after this procedure is still better than just using the real data alone. But there's diminishing returns from using additional synthetic data, and actually like they're having a very careful amount of balance between the real data and synthetic data is more effective than using an endless supply of synthetic data. Do you agree with that interpretation?
I just feel like that means the model collapsing is just an exaggeration of what exactly this is.
I agree. Yeah. I mean, this paper, I think has been, it's like, it was in the New York Times, like people, I think it's gotten a lot of popular attention. And I think that the actual claim is pretty specific, but it's still relevant to practitioners. Yeah, and this actually brings me to some open questions that I think are really interesting and I would challenge you guys to think about. And one of them is, how can we avoid negative feedback loops like this quote unquote model collapse? In a perfect world, if you have a model that is both good at learning and good at generating data, then you might see like just a monotonically increasing curve here, at least up to a certain point. And I guess why is that not possible right now is a kind of maybe an open question that we don't fully understand. Some other really interesting questions are, most of the work I've shown so far, we have, except for maybe some of my own work has used other forms of data, but typically we take a model that is really good, we have it generate data, and then train a model that is not as good to be as good as your teacher. But how can we learn to be better than a teacher? How can we do distillation in a way that the student can outperform the teacher? I think that this paper presents a potential way to do this, which is that you can take that your teacher might be bad at a task, but it's good at another task that can be used to learn. But I still think that this is not fully understood as to how this might be possible or whether it is possible in general. And then lastly, something I did not go into at all, but I think is a very active area of research is how to have collaboration between human and AI labelers or human and AI data curators to get the best of both worlds. So this one example of this is active learning, where you have an AI that does selects which examples to label and have a human do the labeling. But I think there's a lot more flexibility in the world of LLMs for how to have an AI and a human participate in data curation. Cool. So that is it for the lecture.